Welcome back to another lesson in MCV4U. Today we'll be looking at the vector and parametric equations of a plane in 3-space, or R cubed. So here, again, the vector equation of a plane gives us the position vector OP of any point, given that P is X, Y, and Z in the plane. The equation of a plane, again, features two non-collinear vectors in the plane as basis vectors for the plane, labeled as vector A and vector B. These two vectors are known as direction vectors for the plane. So here, the vector equation of a plane has the form, again, the position vector r. So the vector r is equal to RO, the vector RO, plus S times vector A, S being a scalar, plus T times vector B, and T again being a scalar as well, and S and T both being an element of real numbers. And here we know that, again, vector A, again, is provided for us, and there's, again, three components, again, A1, A2, and A3, and same with vector B, again, there's the three components, B1, B2, and B3. And so here again, we see that based on the vector equation, vector A and vector B are direction vectors for the plane. Vector RO is the position vector of a particular point in the plane, where again, S and T are an element of real numbers, and S and T in the vector equation of a plane are, again, these parameters and are these scalar quantities. Again, there are two parameters because, again, the plane here is two-dimensional. So when we look at the parametric equations of a plane, again, here we split it up into the three different components. Again, we have our XO plus SA1 plus EB1. We have Y is equal to YO plus SA2 plus TB2. And then Z is equal to ZO plus SA3 plus TB3. So here we see that in these. Again, XO, ZO, and YO, and ZO are components of the position vector of a specific point in the plane. And then A1, A2, A3, and B1, B2, and B3 are components of the direction vectors, vector A and vector B. And so here, again, this first one represents the X components of each direction vector. Here, again, the other one would represent, again, the Y component of each direction vector. And then, so this is the Y component. And then these would be the Z component. Okay, so here, if we look at example number 1, it says, find vectors and parametric equations of the plane that contains the 3 points. So here we have A, which is 1, 0, and -3, B, which is 2, -3, and 1, and C, which is 3, 5, and -3. So here, I'll just draw again. Again, X, Y, and Z. So here, if we look at our first point, again, for A, we have it at So what we'll do, we'll label this a little bit. So 1, 2, 3 for x. Do the same thing for y. 1, 2, 3, 4, 5. And we'll label the z as 1, 2, 3. Okay, so here, again, if we label our points, first a point is at 1, so we go x at 1, y value is 0, and then z value is -3. 1, 2, 3. So our a value will be somewhere there approximately. So that's our a value. Our second point, b, which is 2. So go 2 down for z, for the x, -3 for y, and then also 1 for z. Our b point will be, or b value will be approximately there. And then for c, 3. And for y, it's at 5. And then z, it's -3. So here, this would be our c value. Here we can draw our vectors. Okay, so here, if we look at our vector A, that can be represented as vector AB, which is B minus A, and so that's equal to 1, -3, and 4. And for vector B, that can be represented by vector AC, and that would be C minus A, so that's equal to 2, 5, and 0. And so here, position vector R will be equal to our point. So we have 1, 0, and -3 plus S times our position, our vector A, which is 1, -3, and 4, plus T, and then our vector B, which is 2, 5, and 0. And again, here, S and T are element of real numbers. And so here, that's the vector equation, and then our parametric equation. So here, highlighted in yellow will be our x components, highlighted in pink are our y components, and then highlighted in blue are our z components. So here we have that x is equal to 1 plus s plus 2t. And then we have y is equal to -3s plus 5t. And then for our z component, that's equal to -3, and then plus 4s. And so here we see again that there's nothing again at the end for e, again, because it is multiplied by 0 there. So again, for the y, same thing. Again, because for the first, again, component, again, 0. So no need to write anything there. Okay, so here, those two areas are left blank. And we'll just indicate that there. Okay, so here, again, just a note, vector and parametric equations of a plane are not unique. Again, there's no such thing as a symmetric equation of a plane. Okay, so example number 2 says, does the point 4, 5, and -3 lie in the plane? And here vector r is equal to 4, 1, 6 plus p 3, -2, 1 plus q, -6, 6, and -1, where again p and q are an element of real numbers. So the first step we want to do is we want to find the parametric equations. And then number 2 is you want to sub in the points and determine the parameters. Okay, so here again, we have, again, 3 parametric equations. Again, because we have our 3 components. So again, 3 parametric equations. Again, we can use 2 of them to solve for P and Q. And then we'll use the third to verify the equation. Okay, so here for our x component, we have x is equal to 4 plus 3p minus 6q. We have for y component, we have y is equal to 1 minus 2p plus 6q. And then for our z component, we have 6 plus p minus q. So here we're going to use our x and y components. To solve, again, we're going to use here our system of equations. So here, again, we have our point 4, 5, and -3. So here we'll sub in 4 for x is equal to 4 plus 3p minus 6q. And for y, we'll sub in 5. So we have 5 is equal to 1 minus 2p plus 6q. Here we have -6q and positive 6q. So we are going to we'll add these 2 equations together. And so that will leave us with 9 is equal to 5 plus p. And then the -6q and positive 6q will cancel out. Here we get p is equal to 4. So now we can sub that back in to our equation. So here we have 5 is equal to 1 minus 2 times p, which is 4, plus 6q. And here we'll get 12 is equal to 6q, and q is equal to 2. So we get p is equal to 4, q is equal to 2. And here, if we again verify the z equation, so here we have -3 is equal to 6 plus p, which is 4, minus q, which is 2. So -3, again, does not equal to 8. So what we can imply here, or we see, is that the point 4, 5, and -3 does not lie in the plane. So example number 3 says find the vector equation of the plane that contains the two parallel lines. So line 1, vector r is equal to 2, 4, 1 plus t, 3, -1, and 1. C is an element of real numbers. Line number 2, vector r is equal to 1, 4, 4 plus s, -6, 2, and -2. Again, s is an element of real numbers. Now here again, we see that the vector equation, we're determining the vector equation of the plane that contains the two parallel lines. Okay, so here again, the two parallel lines, that's what we are again determining here for the vector equation. So here we see that the slope again of line number 1, or the vector m1, will be equal again to the slope of the second line, or vector m2. So here we see that again 3, -1, and 1 will be equal to -6, 2, and -2. And we see that because if we divide again that by 2, that'll be equal to 3, -1, and 1. And so here we see that again, we'll draw a plane here. So if we draw a plane, so here if we draw a plane, again, line 1 will be here. So line 1, we see that for A, it's at 2, 4, and 1. So that's A is 2, 4, and 1. And then for line number 2, again, the point here for B is at 1, 4, and 4. If we draw our line here, that will be represented as vector B. Okay, and so here, again, we represent this, again, using our vector B, again, here. Again, because we need, again, another distinct direction vector. And so here, again, we can use vector m1 is equal to vector A, and then vector B doesn't represent anything right now, so we'll use that again, represent the vector between the two given points on each line. And so that again, will be represented as, again, our vector AB, which is B minus A, which here is equal to -1, 0, and 3. So here, if we write our vector equation, we have our position vector, which is equal to 2, 4, and 1, plus S times 3, -1, and 1, plus T, -1, 0, and 3, which we just found from vector AB, or here representing as vector B. Here again, S and T are an element of real numbers. So we have example number 4. It says a plane. So plane represented as pi. Many times we can, again, use pi to represent the idea of a plane. So here, even when we look at our drawing, again, we can label this as pi. So that represents, again, the plane. Okay, so a plane pi has position vector r is equal to 6, -2, -3. Again, plus s, 1, 3, and 0, plus t, which is 2, 2, and -1. And s and t are an element of real numbers, again, as its equation. Determine the point of intersection between the plane pi and the z-axis. Again, here again, we see that pi is the symbol used for naming planes. Here, if we look at our vector, again, m for the line in the z-axis, we see that that would be represented as, again, 0, 0, and 1. And again, this is the point on the z-axis. Again, that can be represented as A, and here again, Z, 0, 0, and Z. Okay, so again, here we see that if A is a point of intersection, then A also lies on the plane. So here we can write our parametric equations. So x is equal to 6 plus s plus 2t. Y is equal to -2 plus 3s plus 2t. And then z is equal to -3 plus 0s minus t. And here, again, since x is equal to 0 and y is equal to 0, again, we'll use these values to solve for s and t. Okay, so here, system of equations, we have 0 is equal to 6 plus s plus 2t, and we have 0 is equal to -2 plus 3s plus 2t. Here, we're going to subtract our two equations, and we'll be left with 0 is equal to 8 minus 2s. Our two t's will cancel out, and here we get s is equal to 4. Now we can sub that back in to our equation. We have 0 is equal to 6 plus 4 plus 2t. So we get negative 10 is equal to 2t, and t is equal to negative 5. Okay, so again, here, so since here we know that point A is a point of intersection, we can use these values that we just found of s is equal to 4 and t is equal to negative 5. Use these values of s and t to solve for z in the third parametric equation. So here we get z is equal to, again, negative 3 plus 0s, so nothing for s, minus t, which is minus negative 5. Z is equal to negative 3 plus 5, and z is equal to 2. And so here, therefore, we know that point A will be equal to 0, 0, 2. And here, so the last example, so example number 5 says, determine the vector and parametric equations of the plane containing the point P, 1, negative 5, and 9. And the line L, which is represented as position vector R, is equal to 1, 1, 1 plus S, negative 1, 1, and 0. And here again, so here we see that negative 1, 1, and 0 will lie on the xy plane. And here, again, that means that our slope here, or again, our direction vector m will be negative 1, 1, and 0. So here, if we draw, again, our diagram or on our plane, so remember, our plane is represented by pi here. Here we have m a as 1 point, which is at 1, 1, and 1. So that would be A. Have point P, which is at 1, negative 5, and 9. So we'll represent from A to, again, point P as vector B. And then we have our line as well. We have our line that goes all the way through, represented as L. And again, here our direction vector M, which is negative 1, 1, and 0. And so here we see that, again, vector AP, which is represented by vector B here, is equal to, again, 0, negative 6, and 8. And divide that by 2. That will give us 0, negative 3, and 4. So here, I, which is our plane, position vector R will be equal to 1, negative 5, and 9 plus S, 0, negative 3, and 4 plus E, negative 1, 1, and 0. So that's our vector equation. And then our parametric equations. X is equal to 1 plus 0s, so just 0, and then minus 1t, so minus t, that's for x. Y is equal to negative 5 minus 3s plus 1t, so plus t, and then z is equal to 9 plus 4s, and then plus 0t. So those are vector and parametric equations for this plane containing the point 1, -5, and 9 that lies on this line.